So two reactions under our belt, the HVZ reaction and the amination reaction. And we're getting ready to talk about our third reaction for amino acids, and this one is a doozy. So before I even tell you the name of the actual reaction itself, I want to spell it out. So get your pen and paper ready because this one is quite a lengthy name. And it starts with a capital M with a hyphen. So the capital N is basically referring to maybe nitrogen, because that's typically what we have seen over and over and over in organic chemistry. If N is in front of something, then it's probably referring to maybe an amide. We kind of saw that in the amide nomenclature, and that is referring to how the groups are attached to the molecule, and we see maybe something attached to the nitrogen here. So maybe that's the same case. We'll see when we take a look at the reaction, but this reaction starts off with a pH, so a F sound, right? And then what comes next is thal, so THAL, IMIDO, MALONIC. And then we're not done. This is called Ester synthesis. Now, don't ask me why they do not have a shorter hand or an abbreviation for the N-phthalidomide malonic ester synthesis, but they don't. So phthalimidomalonic ester. Phthalimidomalonic ester. Say that 5 times fast. I'll give you a cookie if you can. So N-phthalidomalonic acid, or ester synthesis. Okay, see, look, even I get messed up sometimes on these reaction names because they're a tongue twister most of the time. Okay, so we've got to talk about this reaction, and we've got to kind of understand what it does, and we've got to see what kind of things it has in store for us. And most of the time, what we start off with, the steps of the reaction itself, is what we call an alpha bromomalonic ester. So this is kind of our starting point. Alpha bromomalonic ester. So an ester we know is a C double bond O group, right? And it has some kind of R group that's out here to the side, and this is what contributes to an ester group. Now the alpha position of the ester group, well, that would be here at that carbon. So this is my alpha carbon. And the name of alpha bromo basically means that on the alpha position, I probably will find a bromo group, and I do. But is this all to the molecule? And the answer is no. This is actually a double molecule, so it's a very symmetrical molecule. I see kind of the same group on both sides of the alpha carbon. So I see this carbon sandwiched in between two carbonyls, and the carbonyls are fighting over the electrons, and I see some delocalization that can take place. That bromine in the center, in the middle, this bromine, well, that's good news for it, because if this bromine leaves, this molecule can get electrons, and these electrons can kind of circle through this whole delocalized network system. So if we can maybe attack that carbon and force that bromine to leave, because it's a good leaving group, by the way, already in the beginning, then we can persuade this molecule to go forward in a reaction for us. So there is the alpha bromomalonic ester. That is the starting kind of feature for this reaction. Now, we have now taken care of the malonic ester portion of the name of the reaction. So what about this thalidomide? How do I bring in the thalidomide? Where does it come from? What does it look like? Well, thalidomide is actually a benzene ring, so we'll start off there. And then off of this benzene ring is a 5-carbon ring, and this 5-carbon ring is heterocyclic. So that means at one of these locations I don't really have a carbon, I have a nitrogen instead. I see a double bond O here and a double bond O there. This nitrogen carries with it some free pairs of electrons, and its formal charge is negative. And this is the structure for thalidomide. Now, most of the time this will come to us in form of a salt, so it's not uncommon to see sodium out in front to balance that negative charge, or potassium out in front to balance the negative charge. That is what we would call the salt, and we would take the thalidomide salt and we would kind of incorporate it into the reaction. Okay, so we're going to take these two things and they're going to react. Now, I told you that we're not really going to be focused on mechanism, and we're not, but I at least want to show the first part of the curvy arrow mechanisms. It's not something that I would ask you to do on an exam because we've already said we're not looking at mechanisms this semester, but I at least kind of want to talk about what goes on here. So this carbon, this alpha carbon position, it's getting electrons pulled this way, and it's getting electrons pulled this way, and it's getting electrons pulled this way as well. So this area is a positive area for the molecule right here at this carbon, and this nitrogen is a negative part, right? And we already know curvy arrow mechanisms kind of tell us that negatives attract to the positives, and I see an attraction that happens between the nitrogen in the thalidomide and the carbon involved in the malonic ester. And when this attraction happens, it persuades bromine to leave, and it takes the electrons and it goes along its path and along its future, and it grows up and it becomes a very successful atom. But anyway, there is the kind of first part of the mechanism. Now this is where I'm going to kind of stop, because there's going to be some other steps of the mechanism that are involved. Quite a few of them actually, 2 or 3 more steps. And if you want to take a look at those, the book does detail those for you a little bit, but it's just something that we're not going to get into. But that's kind of the initiation process between the bromomalonic ester and the thalidomide salt that I bring into the picture. What I end up with is going to be an amino acid. So we're going to end up with a C double bond OOH, a carbon, an NH3 plus, and then a R group, whatever R group that is. Now, where does the R group come from? Where is the R group going to be found? Well, it's going to come from your starting reagents, actually. That's typically what we see. That's typically how you pick the amino acid that you want to make, and that's where the R group is going to come from. So you just got to be very careful, because this is what distinguishes between all of the amino acids, and if we can change that R group, then we can change the amino acid structure for it. Another variation of this reaction could also involve, in the mechanism, bringing into the picture a R prime Br. And this R prime Br is an alkyl bromide. And this alkyl substituent could also be the actual substituent that goes here onto the amino acid. So you really have to look for the bromide. If that's the version that they're giving you, you look for that bromide molecule, and wherever that bromide molecule is, that is the R group that gets attached to the amino acid itself. Okay, so this is actually the version of the reaction that you're going to see most often in the text and in the homework and in the test and the quizzes and everything else that comes your way. It's going to be this version. So very often they'll kind of take this thalidomide, they'll tell you it's a thalidomide reaction, malonic ester reaction, or whatever the case is, and they will give you maybe an alkyl bromide, and that alkyl bromide might just be CH3Br. right? And they want you to react that with all of the other stuff that we've mentioned up there from up above. Well, that means that this CH3 group is going to go on to the structure of the amino acid, and that's the structure that happens every time from the malonic ester synthesis. So that's the structure that happens. Find your alkyl bromide. The alkyl group will tell you the R group that gets plastered on, and this is just a CH3 group, and we know that the alkyl group for CH3 again is alanine, so ALA or A. And that's kind of the simplistic version of the malonic ester synthesis, and that's kind of how we'll stop it. So again, you're going to be given the task. This is a malonic ester synthesis. You'll be given the reagents. You'll take a look at the reagents. Understand that you're going to end up with an amino acid after the mechanism is over. You're going to end up with a carboxylic acid, an alpha carbon, and a NH3 group. And off of this alpha carbon, you look for that alkyl bromide that they will tell you in the problem what they've used. You look at that alkyl bromide, and whatever alkyl group is there on that structure, that is what determines the type of amino acid that you've made. So if that's a methyl group, it's alanine. If that's a hydrogen, then it's going to be glycine. If that is a isopropyl group, then that will be valine. So you get the picture, you get the drift. It's the same as always before. You modify the R groups, and that will tell you the amino acids that are there. Okay, so that's all that we need to mention about the thalidomide-malonic ester synthesis, right? So in the next video, we'll take a look at what we call the Strecker synthesis. Again, this is something that's not new. We've actually seen Strecker before in previous chapters, but we'll go through, we'll take a look at Strecker, we'll kind of review what that was all about, and it's another way to make an amino acid. And then guess what, folks? We're done with the mechanisms and the reactions of the chapter. So only 4, and they're all really doing the same type of product. It's this amino acid template. It's just different ways to put the R groups onto those structures. That is it. That's the only difference between all of these reactions. So stay tuned. One more reaction. You can watch this next video. You'll be finished with the reaction parts, and then take a break and maybe come back a little bit later to look at maybe peptide and disulfide bond chemistry. But at least make it through the next one. You're almost done with reactions, so why not? Have a little fun.